Hey, this is Ben Sherman. I am delighted to tell you about my work together with Jesse Michel and Mike Carbin on a differentiable programming language semantics that we call Lambda S, which is a differentiable programming language that supports higher order functions and data types. So let's jump right into it. Here are the contributions of our work, and I'll go into these in more detail throughout the talk. So Lambda S is the first differentiable programming language semantics that supports a bunch of features all in common. It supports higher order functions, higher order derivatives, and Clark derivatives, which are a particular semantics for derivatives of non-smooth functions like min and max. Given the support for these higher order functions, we support the semantics for particular higher order functions of integration, root finding, and optimization, all of which are important in applications in machine learning and differentiation and other contexts as well. Our semantics is computable, and accordingly, we provide an arbitrary precision implementation that we've implemented in Haskell. And at the end of the talk, I'll tell you a bit about some smooth libraries, everything that you can differentiate through for constructing and computing on 3 higher order data types, which are related to these higher order functions. And these data types can represent implicit surfaces, generalized parametric surfaces, and probability distributions and measures. Okay, so let me get into a little bit more detail just about what all of these things mean. So we might want to differentiate expressions that involve operations that we consider higher order functions. And so let's look at some particular higher order functions. These can include optimization. For instance, we might maximize a function in a given expression, and we might want to take a derivative of that maximization operation. We may have integrals in our expression, and we might want to differentiate through integrals. And we also might have root finding, where we want to differentiate through the solutions to the roots. And so these might seem just like these abstract examples, but these are 3 examples of higher order functions that are useful to keep in your head. And they come up in machine learning, for instance, as well as other contexts. For an optimization, we see optimization come up in adversarial training objectives in deep learning, for instance. Integration comes up all the time when we want to take expectations over random draws. And root finding comes up when we want to learn implicit surfaces, for instance. And that can occur, for instance, in computer vision. So there are several papers, papers and papers that come out in the machine learning community about, all right, like how do we differentiate through these operations? And it kind of seems like a bespoke special thing, but here we see like these are just higher order functions, and we can talk about the derivatives of these higher order functions, and we can implement them essentially like once in a language semantics, and then let programmers just write them and compute derivatives and get what looks like some special kind of stuff, but should just fall out, just like the derivatives of normal functions fall out when we implement it for an AV system. So I'll get into that a little bit later. Okay, so what does arbitrary precision mean? So I mentioned that our implementation is arbitrary precision, and that means we can evaluate any expression in the language to as much precision as we'd like. So when you type an expression at the REPL, you not only type the expression, but you give a tolerance. And it returns an interval, a lower bound and an upper bound, that's guaranteed to include the true number within the interval. And its width is at most the tolerance that you specify. So you can specify a tighter tolerance, for instance, 10 to the negative 16, and you'll get an even more refined interval. And you can get one as fine as you would like. Okay, so at the end of the talk, I'll get into some libraries for differentiable programming, and we'll look at 3 example tasks that use these libraries. One will be to look at how the clearance distance of a car from an obstacle changes as you move the car. So that's an example of operating with shapes. And then we'll have another example of operating with shapes, a little different representation of shapes, where we ask about a differentiable ray tracing problem. So we ask if we make a tiny perturbation to a scene, how does a tiny perturbation to the output result? And then we'll also look at probability distributions, where if we imagine a family of probability distributions and we perturb the distribution, how does its properties, such as mean and variance, change? So all of these, right, we want to compute these results, which involve higher order functions, which already itself is interesting, particularly when it gets to arbitrary precision. And then we want to take derivatives of these operations. Okay, so here's the outline for the rest of the talk. First, I'm just going to sort of give you a bunch of examples of typing things at the REPL for lambda s so we can get some intuition for how it works. Then I'll get into a little bit more detail about how it works, and in particular, the three key features that it supports: higher order functions, higher order derivatives, computability, computable semantics, and derivatives of non-smooth functions. And then I'll get into those higher order data types and libraries. We'll look at an example task in each for implicit surfaces, generalized parametric surfaces, and probability distributions and measures. Okay, so as I mentioned before, we can compute expression like pi. We get an answer that has an interval that contains the true value of pi. And we can evaluate this to as much precision as we would like. We can also compute values, of course, like sine pi. And here's what happens when you have arbitrary precision. We see that we don't get exactly 0, but we get an interval that includes 0, and it'll get as fine as you go. You'll get finer and finer intervals that include 0, and so this is equivalent to 0. So unlike if you plug this in at floating point, you might do sine pi, and you actually won't get 0. You'll get a number very close to 0. In lambda s, sine pi is actually equal to 0. They're equivalent programs. You can substitute one for another because basically they're each compatible with each other. The intervals that they return, the sequence of intervals that they return eventually include each other. So this is an advantage of having this arbitrary precision arithmetic, that we get real equivalences in our programming language, for instance, of sine pi equals 0. So that's just a tangent, not even getting into the differentiability stuff, but already some interesting things come up when we're looking at computability. If we try to do 1 divided by sine pi, we're just going to get non-termination, because we can't actually tell whether sine pi is 0, or maybe it's this thing that's like just larger than 0. So unfortunately, we kind of get non-termination, but this is a key aspect of the language and of its semantics. And again, the key thing is sine pi is equal to 0, so we have to get the same behavior whether we write 1 divided by sine pi or 1 divided by 0. Okay, so we have higher order functions. So here's a simple example. So we can compute the integral of the function x squared over the unit interval 0 to 1, and we can get a result. And of course, just like any other operation in this language, we can compute it to arbitrary precision. So we can compute it to a finer precision as we'd like. So these are higher order functions. Okay, so let's get to derivatives. So sine pi is 0, and derivative of sine at pi is -1. And here again, we get an approximation. And here's cosine of pi, and we know the derivative of sine at pi is equal to the cosine of pi. And again, this is an equality in our language. So we can compute higher order derivatives. This just comes out of the fact that this deriv operator is just a first-class function in the language, just like any other function. So we can apply it to itself, for instance, and we can take the second derivative of sine at pi, which is again 0, as we see. And just naturally, by again using the derivative function and the fact that we can nest it under binders, we can compute mixed partial derivatives, for instance, here. So here, this is a second derivative with respect to both x and y of the product x times y at x equals 0 and at y equals 1, and we can get a result. All right, so let's get to a slightly more complicated example, and this will start stressing the semantic aspects and showing how lambda s is unique. So this example is the same example that I discussed in the 5-minute talk. So suppose we just have a simplified path planning task for an autonomous car. We want to maximize its clearance, which is its distance to the nearest obstacle. So we might imagine we want to optimize that with gradient descent, meaning we might want to imagine making tiny perturbations of the car's position and asking how that will affect its clearance, and then taking steps in the direction of the position that will improve the clearance the most. All right, so let's make it concrete. Our autonomous car is just this point, the blue dot, and the obstacle is this L shape. So the clearance is represented by the red dashed line. And now we can ask a question: how does the clearance change, for instance, if we increase the y coordinate of the car? And the question is a rate of change question, right? That's what the derivative is about. As I increase y0, how does the clearance decrease, right? We can see it's going to decrease. So here's the mathematical function defining the clearance distance. It's just a minimum of, and I'm just using square distance because it's a little bit easier. It's just a minimum of the square distance to all the points in that obstacle. And the points in that obstacle we can represent as two line segments, so we'll take the minimum over the distance to the two line segments. Okay, so what we would like to do is take this function f, which, as we can work out in the vicinity of y0 equals 0, it becomes this simple expression, and we just want to get the derivative of f at 0, which it turns out is -2. If we use these algebraic laws, we can see that that's the case. Unfortunately, no current semantics for differentiable programming would let us express f because it's got some tricky aspects going on. First of all, minimization is non-smooth. Sometimes it's not differentiable when the arguments of the minimization are equal. And the minimization over the unit interval is a higher order function, where semantics can be a bit tricky. And thinking about the derivative of such an operation is also tricky. But we can do it in lambda s. So here we define the f function in lambda s. It looks exactly like the math. We have a min operation, we have a min over the unit interval operation. Both of these are primitives that are built into the language of lambda s. And here's our evaluation at the REPL, where we compute deriv of f at 0, and we compute an interval that we can sort of empirically see is -2. This is evaluated to a certain precision. As we get finer and finer, it will converge on -2. So min, min01, and deriv are all essentially primitives built into the language. But they can be composed in any which way, and they give interesting behavior that allows us to actually compute properties like this. So what is lambda s, the language? You can think of lambda s, it's just the simply typed lambda calculus. So the basic functional programming with some primitives. So here are the arithmetic primitives. So we have a bunch of first order functions, and none of these are particularly special, but for every primitive we have implementation that I'll get into later. Sort of each primitive, you need to implement certain things to make it work as a piece in the language. The key thing that makes it neat are these primitive higher order functions that we have in here. So we have primitive higher order functions for integration, for root finding, and for optimization, which are the 3 higher order functions that I talked about earlier in the talk. Here are the primitives that correspond to differentiation. Now, I'm really not going to get into these in the talk. These give you really sort of general capabilities for differentiation on different types and things like that. We can talk about derivatives at more complicated types, but really it's sufficient to just look at derivatives of real valued functions, and that'll work for us for now, because sort of it's nice to have the intermediate types for constructing a computation, but at the end of the day, we're asking questions about quantity and number, and that's where the real numbers come in. All right, so let's get into how lambda s works. Lambda s really builds on related work. It combines 3 different approaches that give 3 different features that we want to combine. And the combination is a bit subtle. It's not like you just put these 3 things together, but really key that it builds on techniques leveraged by these 3 other papers. So for higher order derivatives, It's based on this really neat blog post by Connell Elliott about higher dimensional, higher order derivatives. So it's, really, how do you represent higher order derivatives? For higher order functions, the semantics is really based off diffeological spaces. It's, effectively just kind of categorical techniques for taking a category that doesn't have higher order functions in it and extending to one that does. And then for computability and non-smooth functions, it's really following from works of like Antonio and Adelot, a language for differentiable functions, and really about this idea of a connection between the Clark derivative and interval arithmetic. Okay, so let's get into these three pieces of how lambda s works. So the first thing we'll start off with is, how do the higher order derivatives work? Basically, any first order function in the language semantically corresponds to a derivative tower. Think of it as a stream of all the kth derivatives of a function. So if you have a function, right, its internal representation in the language is basically functions for computing not only how it acts on values, right, how it is as values, but it's also its first derivative, its second derivative, third derivative, and so on. So every function is really this tower of all the functions for its derivatives. So that's kind of a little bit scary because every function is really infinitely many functions. So how do we specify them? Here's an example. So here's multiplication, right? So just as we expect, if you have to specify infinitely many things, you better do it in a finite way. We can use recursion. So we can specify, there's a neat recursive way in which we can specify the multiplication operator as a smooth function. We give its value, and then we give its derivative as a smooth function in a productive kind of recursive way. The value level is pretty simple. It's just we multiply the values. It's just, reduces to a more basic notion of multiplication. But the derivative is interesting, and that's where we have the product rule come in, right? That's the key feature of calculus. And on the right side, we're, referring to smooth multiplication, which is what's actually being defined in these two equations. So that's where the recursion is going on. And it's really, this recursive pattern is exactly like defining a stream of natural numbers, 0, 1, 2, 3, 4, so on, in the following way, right? We say the first value, and then we say the rest of the stream as a stream itself that refers to the stream of the entirety of the natural numbers. So it's exactly like this. And a lot of our semantics is actually using this kind of recursive aspect to define infinitely many things at once. Okay, so how do we support higher order functions? So I said what a first order function is. It has all its higher order derivatives, but now what does a higher order function mean? Well, second order functions are just going to be transformers of first order functions. Even higher order functions, there's, you just kind of follow the pre-chief stuff, but to get a good intuition, second order functions are the key. So second order functions are transformers of first order functions. And this key thing comes up where they quantify over this context gamma. So think of gamma as being this collection of other smooth variables. And you want to be parametric. You can say like, well, you can have any other smooth variables. If you have a function that involves a bunch of smooth variables, and then this other variable that we're going to bind over, we need to give a function that only depends on the smooth variables and gets rid of that bound variable. Kind of confusing. Here's an example. What about integration, right? That's our simplest higher order function, right? And what this is doing is, if you give me a function f, I tell you what the integral is. So what the rule says, right, the meaning is that we have to, for any gamma and for any function f that takes a collection of variables gamma and a real number, think of this as the x that comes in that ranges over 0 to 1 and returns a real number, I should just give a function that depends on the smooth variables gamma and basically integrate out this real number here, which stands in for the x. So what do we do? Well, our output is a smooth function from gamma to r. And what that means is it should be a collection of kth derivatives. So the kth derivative of the integral of f, well, what is that? It takes in the value and k infinitesimal perturbations. That's how we represent a kth derivative. And then it returns a real number, and it's just going to actually integrate the kth derivative of f, which, remember, it takes both a gamma and an x value, so gamma and x, and then the perturbations, we perturb gamma but not x, because x is just this thing being integrated. It doesn't have any perturbation here that comes from the gamma. It's integrated out. The paper hopefully explains in more detail if it's hard to kind of get that. Okay, now I want to just briefly touch on the computability aspect and how we view derivatives of non-smooth functions, though I really don't have the time to treat this in great detail. So internally, I've been talking about, these functions and streams of kth derivatives that, where each of these functions are these numerical operators. We should think of these numerical functions in terms of themselves being a little bit interesting. So values that we operate are we can think of as streams of increasingly precise approximations, right? Intervals getting finer and finer. And then first order functions, again, these are the implementations of first order functions. So if you imagine like multiplication, right? So multiplication, there was the smooth function, and that referred to the continuous map for its value level definition of just a value level implementation of multiplication. Well, the value level implementation of multiplication is itself this thing that's a stream transformer, right? If you give inputs that are streams of intervals, you get for the things you're going to multiply, your output will itself be a stream of intervals. So this is how we get the computability aspect, and it ties in very nicely with the derivative of non-smooth functions. So let's look at this function ReLU. We can implement this in lambda s and get some nice differentiability behavior. So it's differentiable everywhere except for x equals 0. So when x is positive, the derivative is 1, and x is negative, the derivative is 0. Well, what should it be when x is exactly 0? By a continuity aspect, we really say its behavior has to be compatible with both 0 and 1. So it's really hard to have a good answer here. And indeed, if you look at the implementation of lambda s, you get this funny kind of value when you try to compute the derivative of ReLU at 0. It's this interval that never gets any finer than 0, 1. Because if the input were slightly less than 0, it would have to collapse to 0. And if it were slightly bigger than 0, it would have to collapse to 1. So it kind of gets stuck here, giving a 0, 1. And this corresponds to the Clark derivative, which is independently developed to give sort of useful results when thinking about derivatives of non-smooth operators, like things like max and min. And you know what? The thing is that's great about these non-maximal values, these intervals that sort of never get fine enough, is sometimes they're good enough. So what about the derivative of ReLU of x squared? Right, so that's going to be flat, and then it's going to be a parabola, just x squared. Well, the derivative of that at 0 is indeed 0. And it just works out basically using this interval arithmetic that we multiply 0 by the interval 0 to 1. And so the interval 0 to 1 kind of cancels out, and you get an answer. So we get this differentiability behavior that's really tricky to get without using Clark derivatives. Okay, so finally, let's get into some examples, libraries, and tasks that we can do using lambda s. All right, so here's another example of differentiable ray tracing. So in computer vision, we may want to, we may have a scene and we might imagine, this scene that gives us an image, and we see the image and we want to optimize the scene to reproduce the image as best as we can. So to do that, we want to differentiate through the ray tracing operator. So imagine we have a ray of light coming from a source that bounces off a circle before hitting the camera. How does the brightness change when we move the circle up? That's a differentiation question. Now, this gets really neat because there's a lot of stuff going on, right? To do ray tracing, what we have to do is we have to find the intersection of this line with the circle. The circle may itself be implemented as an implicit surface where it's represented by a function, so we need to compute where this function is 0, and then you need to get the angle that it bounces off, and there you need the surface normal, which is going to come from looking at the derivative of that function at the intersection point. And then, so what other things affect the brightness? So not only this angle, but the length of this line segment and the length of that line segment. So all those things change, and the derivative is going to incorporate all of them. So in lambda s, we can compute the brightness of the reflected light, for instance, of this circle. And we can see that the brightness would increase if we move the sphere up, and we get a good approximation to the rate at which the brightness increases as we move the sphere up. So how does this work? Okay, it's a slide full of code, but really this is all the code you need. You don't specify any derivatives manually. The derivatives all work out just from the implementation of this with components, which are all themselves differentiable. Okay, so where are the key things that come in? When we're doing ray tracing, we have to basically take our implicit surface and we need to find where the intersection point is. And we can do this with root finding. The implicit surface is basically a function that's positive outside and negative inside, so we just need to find where it's flipped sign. And we can do that with this first root function, which is a primitive implemented in lambda s. And we can take the gradient of s to get that surface normal. So this is the ray tracing function, right? It says given a scene, you get a real number. And because we've implemented in lambda s, we can compute its derivative. And what's neat about this is there's already a derivative function actually already in this definition. So when we compute the first derivative of ray tracing, we actually will be computing the second derivative of the function defining the implicit surface of the sphere. So that's like a fun little fact. So here's the library for implicit surfaces. We can compute unions, intersections, complements, and this is one example of higher order functions as, data types that are higher order. Okay, generalized parametric surfaces. This is going to be taking, basically abstracting a little bit that car example with the clearance. So here's another clearance example where now the car has become this little bubble. And again, there's more things that affect that are interesting because now the closest point on the car can change as you move the car. And so the clearance is originally square root 2 minus 1. We can compute the clearance and we can compute that it decreases when we move the car up. And we can just implement this in lambda s. And the way we do that is with these higher order data type that we call minimizers. You can represent a shape by its minimization functional, right? You say this shape, this collection of points, you describe it by saying, if you give me some function f, a real valued function, I'll tell you what the minimum value of it is over my entire shape. And this forms a monad. And we can do things like compute the clearance, right, between two shapes implemented as these minimizers. And we can do fun things like compute convex holes, and we can describe triangles. And so this lets us describe the shapes that we showed there in that example. Right, so the car, we can just apply a function to create a sphere from the unit interval, and the obstacle is just the union of some unit intervals, and it works out. Okay, finally, probability distributions, right? Suppose I have a probability distribution and I perturb it a little bit. How do the mean and the variance change? Well, if the mean is going to increase and the variance remains constant when we tilt the distribution in this way, right? Obviously, the mean is going to increase, but it's interesting that the variance remains constant. And again, we represent measures in probability distributions as these integrals. Given a function, I'll tell you what the integral of the function is over my measure or probability distribution. So this again forms a monad very nicely. We can define mean and variance in the straightforward ways by just computing the integral of functions over those distributions. Okay, so there I've given you 3 examples, and Here's just a reminder of the contributions. The paper has more. Thank you for listening to the talk.